Hello everyone. In this lesson, we will delve into the third part of the glazing process, the drying method and mechanism of varnish. In our previous class, we learned about different types of coating methods. Based on the type of varnish used, coating can be divided into solvent-based varnish, water-based varnish, electron beam (EB) varnish, and ultraviolet (UV) varnish. Today's focus will be on understanding how each type should be dried. First, there is solvent-based varnish, which is generally dried by hot air or infrared drying methods. Water-based varnish follow a similar drying method as solvent-based ones. Electron beam varnish, also called EB varnish, requires special electron beam drying techniques, while UV varnish, also known as ultraviolet varnish, needs special ultraviolet drying processes. Now let's learn about the mechanisms of different drying methods to deepen everyone's understanding of the varnish drying process. The first mechanism is hot air drying. External cold air is transmitted to the heat exchanger by a fan, where it is heated by electric heating and transformed into hot air. This hot air is then transported to the surface of the printed material. When the surface coating absorbs the energy of the hot air, its temperature rises, molecular movement accelerates, and solvent molecules and water molecules in the coating escape, achieving the drying effect. The efficiency of hot air drying is related to wind speed, with common hot air dryers operating at wind speeds between 20 and 50 miles per second. Infrared drying refers to using infrared rays to dry the surface coating of printed materials. Its drying mechanism is as follows. When infrared rays irradiate the printed product's coating, part of the infrared rays are reflected by the coating surface, and the rest penetrate into the coating. Of the infrared rays entering the coating, some pass through, while the remaining part is absorbed by the coating, converting into heat energy. This raises the coating's temperature, causing solvents and water molecules to escape. It should be noted that the wavelength of the infrared rays must match the performance of the adhesive. Electron beam (EB) drying applies only to printed materials using EB varnish. In this method, charged particles directly impact acrylic substances in paint, producing free radicals, which cause unsaturated double bonds in resin to break. This leads to rapid chain polymerization reaction, resulting in ink curing. Finally, UV drying, also known as UV curing, is only applicable to the use of UV varnish prints. Its drying mechanism involves ultraviolet irradiation causing low-energy photons to impact the photoinitiator in the ink. This leads to the production of free groups in the acrylic substance by the photoinitiator, which then cause a rapid chain polymerization reaction by breaking the unsaturated double bond in the resin. As a result, the coating crossbond film cures. The spectrum distribution table of different bands shown above illustrates that ultraviolet light can be divided into UV-C, UV-B, UV-A, and UV-V bands based on different wavelengths. It is evident that longer wavelengths result in stronger penetration. Therefore, when dealing with thicker coatings, a longer selected drying wavelength should be utilized for optimal results. Let's explore the variances between the following drying methods. The primary distinction between UV drying and EB drying lies in the presence of a photoinitiator. UV drying utilizes a photoinitiator to generate free radicals in acrylic substances, whereas EB drying does not employ a photoinitiator and instead directly impacts acrylic substances with electrons to produce free radicals. The key disparities between infrared drying and ultraviolet drying are as follows. Infrared drying facilitates the escape of solvent and water molecules from the coating by transferring heat, while ultraviolet drying induces polymerization of monomers in the coating through the use of a photoinitiator, thereby achieving curing. Infrared drying is characterized as a physical reaction process, while ultraviolet drying is classified as a chemical reaction process. Additionally, infrared drying results in gas overflow during its process, whereas ultraviolet does not exhibit this phenomenon. Consequently, ultraviolet drying is considered relatively environmentally friendly. The left diagram illustrates the mechanism of infrared drying, while the right diagram depicts the mechanism of ultraviolet drying. It can be observed that infrared drying leads to red particle overflow, whereas no material overflow occurs during ultraviolet drying. That concludes our lesson for today. Thank you for your participation.